Okay, so we're back. Oh. Okay. So everyone is back now, or at least some of them. Sorry, I sort of wait until I see the viewers. Um, and okay, so we will continue now. Um, so I'm hitting screen share, and we'll continue with the slides. All right. Okay, so essentially we can now organize these verbs in terms of a very simple table. There are two basic polarities. Either the verb is related to the production of data, or the verb is related to the consumption of data. And then we have the question of whether the data is ephemeral or the continuation is ephemeral. And the opposite to ephemeral would be persistent, right? So on consumption of data, the data may remain in the database. So that's a fairly standard use of a database, and that verb is to. Someone joined me here. Who is that? Orion. Okay, very good. Thank you. All right, so I'll just continue along. So the name of that verb is read, where data remains persisted in the database. When the continuation is persisted, that's called subscribe. That's a kind of publish and subscribe mechanism, right? So we get, in fact, all of the usual verbs: store and read, publish and subscribe, publish with history and subscription, and also put and get, which are quite interesting in their own regard, where both the data and the continuation are ephemeral. So in that setting, the data provider puts the data, the data reader reads the data consumer reads the data, and when the read gets to the data is transferred from the producer, from the producer's control to the consumer's control, meaning that the producer knows that he or she or it put the data at a particular key. When the consumer comes along, it grabs it from that location, and so the producer no longer has any handle on the data while the consumer does. Now, again, so just to emphasize what I'm saying, when the data is persistent and the continuations are ephemeral, this is traditional database operations and can be made consistent with ordinary transactions where all the transactional semantics is centralized to one store. these operations are traditional messaging operations, including publish and subscribe. And these are quite interesting if you want to do item level locking in a distributed setting. Here's an example. Imagine that we have documents that are stored at keys, and those documents correspond to lists or collections of some kind. And suppose that we have two or multiple, we have n different parties which may update that collection, either adding to or removing from that collection. One way to achieve that with a minimal amount of mess and fuss is that when a consumer goes to a particular resource, one of these lists, it grabs the list and then does its update, right? So, and then puts it back. So since the list is simply we have an incoming. Orion, if I answer this, I have to stop the broadcast. So sorry viewers, I just got an incoming call from Orion. If I answer that, I have to stop this particular broadcast to answer that. So if there's a question or some need to create feedback, please type in the chat window. You can see it's over to the right, and it's enabled if you use the blue one up here. If you're on a mobile device, that's a little more complicated. I don't have a mobile device to show you how that's done, but Hangouts on mobile devices are slightly different. If there is any question or comment, please type it in the chat window, and I'm happy to respond. If you're having technical difficulties viewing this, I'm happy to respond. The only feedback mechanism we have right now is to type in the chat window if you want to ask a question. Okay, very good. That gives us the notion of item level locking. Now, so the question is, how is this related to the interpretation of the logical principle? And the answer is actually quite straightforward. The negation is where we are expecting an A. This is the continuation. The production is, or the A side of things, is when we have an instance of A in our hand, a witness of A in our hand. So you think of the key is the pivot place, and the proposition is really, at this location I observe an A or I don't. That's the constructive interpretation of the logical principle. And this corresponds to a data consistency constraint, which is that at the particular location we can guarantee that a continuation will never be fired unless there is data present. So either at the location we have nothing, we've never seen this location before, or at the location we either have data or we have a continuation. And that's how the logical principle corresponds to a data consistency check on storages that are or stores that are utilized within this network. Now it turns out that this is closely related to, there's a way to connect this all together with some sort of interstitial tissue using the pi calculus. And here's how it's done. What we'll do first, let's go at it from the programmer's side. So let's design a DSL, so a little domain-specific language, following the language integrated query pattern, and we'll have for comprehensions correspond to to consumption, right? And then so roughly speaking, then the general pattern is for E, where E is some event from a given collection, using a particular verb, where the verbs correspond to these semantics we outlined before. You go to the key, that's the location, you check some condition, and so under the condition that filters for those events at those locations from that collection, you then pass it on. So clearly we've got enough syntactic information to have everything here, right? So the for comprehension actually tells us what the continuation is, right? And then the interpretation of the verb is to simply check the presence in the collection at the key of this, and if there is none, it serializes the continuation. So it grabs the continuation, serializes it, and puts it at that key in the collection. So this is, in some sense, a kind of expanded notion of collection than is normally thought of, but it follows rules as we've outlined before. And we'll have the production style follow messaging style. So at the collection, or you can use dot or bang, the verb, and then you put the key in the value. So there's our tiny little DSL, and it turns out if we can squint, we can just make out the pi calculus. Just to make it very clear, what I'll do. Maybe it's clear enough in this slide. I'll go ahead and do it that way. So here's no mouse. So if you look, the for comprehension follows exactly the pattern that we outlined in our DSL, and our messaging follows the. I'm going to have to use the mouse just so that people can see that. If this is too small, let's see what I can do. View, zoom, into window. Hopefully that's large enough so that you can both see it and I can use my mouse. So over here, here's our for comprehension. Here's the receipt of the document, and we can now use pattern matching to take it apart. Here we're going from a particular collection and a particular key. So if you can see my my mouse moving, I'm indicating each of those. This is the continuation that will be handed the event along with the remainder of the computation, and that corresponds to the pi calculus guarded input. And this is guarded input in a pi calculus that is effectively a version of the applied pi calculus. So if you go to GitHub and you look at Special K, what you'll see is a distributed implementation of a pi calculus in which the input patterns correspond to Prolog terms, and likewise the output patterns correspond to Prolog terms. And that's realized in terms of an embedded DSL for Scala. Okay. I'm sorry, Orion. Please, family first. Focus on the little boy. I'm sure everyone understands. And if anyone has any questions about what I'm saying, just feel free to pipe up. So essentially, what we've just done is we've analyzed all of the verbs, and then each of the different flavors, whether this is persisted or not, whether the production data is persisted or query is persisted, are just different flavors of these, and those can correspond to decorations in your verbs, or for programmers usually that means a different name for the verb. Operators and symbols often are confusing for folks. So then over here we have this complete specification of a model of concurrent or distributed programming that has, gosh, over 30 years of quality assurance applied to it. So we know quite a bit about the PyCalculus and what it means in terms of the semantics for programming. And here we have an interpretation in Scala, and then that interpretation is then realized over an architecture that allows you to span and cover all of the traditional models of distributed programming. And in fact, as I said before, with this table, we can completely characterize all of the different models that arise, right? So there are, in fact, even models that arise that are present here that are less often used. So we have a coverage of the space and an understanding of the space that is more complete. It's less random. We see the whole picture, and it turns out to be rather nicely organized. And it makes sense then why we don't have a one-size-fits-all model, because in fact all of these different kinds of domain characteristics show up in different kinds of applications, as we've tried to indicate. Now, what's even more interesting is, if you recall, at the beginning of the talk, I spoke a bit about the need to help the programmer along in terms of providing more typing information and more support from the type systems, so that traditional concurrency problems like deadlock, live lock, races, stuckness, starvation, all of those things, which are actually considerably more complicated than sequential programming. The type system and the compiler can begin to help the programmer of distributed systems along. And in fact, it turns out that there are logics, and I'll just briefly, you don't have to understand all the symbols here. This is taken from Luis Cairas's paper, Behavioral and Spatial Observations in a Logic for the PyCalculus. I just want to show you how small it is, right? It takes exactly one page to specify this logic. The logic, via what's called Curry-Howard isomorphism, turns into a corresponding type system. And Kairas has a number of papers on type systems for the PyCalculus. They apply directly to our results. So in particular, once programmers can program in this DSL, we can import all of Kairas's results and the results of concurrency theory based on the PyCalculus to apply directly to supporting the programmer. So in the interest of time, I'm going to jump around the slides a little bit. Yeah, so just to flesh out that idea, the idea is that a program will end up looking like this, and this ends up being a behavior. This is a concurrent behavior that runs, in a distributed setting, right? So we can actually have multiple different sources generating different streams of events that can be collated and put together. So bids and asks, for example, is a really good. So trading. This is a very nice pattern for trading, right? So that can run on any particular node where this DSL runs. So the typical stack for special KKVDB is a JVM with a Scala runtime, an AMQP infrastructure, and some storage. It could be XML. We have bindings for XML, for XQuery, as well as for Mongo. We plan to have bindings for SQL via the sort of traditional data log interpretation in the not too distant future. So this is the standard platform, and you can have multiple of these nodes running, and they can be organized either in terms of separated networks, or so like the red and blue networks are separated and only joined together at this one node, the white network. And the nice thing is that this behavior can be augmented with annotations that correspond to the types that related to the logic I showed before, and these annotations can be used to catch things like deadlock. So you can actually use these annotations to catch things like a deadly embrace. Now, there are some other beautiful aspects of this particular architecture, and I'll just mention one of them that have interest and intrigue. So the model for the get verb in this distributed setting runs roughly like this. Let's say an application issues a get into a node in the network. The get will check its cache, then it will check its, and if there's nothing in the cache, it will check the store. If there's nothing in the store, it stores the continuation, just as we said, but then it also forwards via some AMQP provider to the nodes that it has acquaintances with. So let's say it forwards it over here. Then again, now we recurse, right? Because now we have an incoming get, check the cache, check the store, and then potentially forward on. Now let's say that that there's nothing here as well. So now there's a potential race, right? So the race is that a provider could put the value here at the B node, right? Let's say that it's the top key that we're interested in. That's the location. So a provider can put a value at this key or this version of the key over here, and one could come in this along. Let's call these nodes A and B. So a provider could supply the data at B. A provider could supply the data at A. So now they're effectively racing to supply the data. Now let's see what happens. Let's suppose, just for the sake of discussion, that A wins because A is local relative to the request. The request came in on A. The provision of the data also came in on A. So let's say that that one wins. Then the data is handed off to the GET request. And in this case, let's say that it's entirely ephemeral. So the GET consumes the PUT request. Now the PUT request at B comes in, and what should happen? Well, what's stored over here is a continuation to return it to the requester, not the original continuation, just a continuation to return it to the requester. So that's exactly what happens. So this follows backwards. And since there is no continuation in this database, all that happens is that the data is now stored over here. So effectively, the data got shunted over here. Now you may think of that as a bug, or you may think of that as a feature. What it ensures is that the data is constantly swimming around in the network. You don't actually know what physical node it resides on. Now you may say, oh, that's a terrible way to consume bandwidth, but the other side of it is that as more and more requests come into a particular spot, data is constantly swimming to where it's most requested. So this architecture just as as a matter of what falls out for free, you get a kind of load balancing and pushing data to where it's most requested for free. So that's a very nice feature, we think, because it ends up having both a security property. It's hard to go and attack a particular node thinking that's where the data resides, because data doesn't have a specific location unless you pin it to that location for a business reason, and otherwise, and then on top of that, data sort of repartitions and relocalizes itself. So locality, it emerges as a function of the application domain semantics itself and the application usage itself, and we think that's a very nice feature of this kind of architecture. All right, so there's 5 minutes left in our discussion. I just want to say what we've done. What we've done is to talk a little bit about an organization of the traditional verbs in a distributed setting that follows logical principles that then fits very nicely under the Monadic API, following the link design pattern. So that has, for us, the advantage has been that you reduce the total number of concepts that are in motion for a programmer. The programmer thinks about collections which may be distributed over the internet and doesn't think so much about where things are stored, but more about the kinds of application domain semantics they need to support. So they have essentially one programming model that, not programming model, but one programming framework or conceptual framework, and they can begin to organize and pick and choose the right programming semantics, whether it's get and put, distributed transactions, messaging, or more traditional storage. All of that's available under one facade. And what we found from empirical data is that when we give this facade to programmers, they are able to build distributed applications in weeks. And that was something that I was happy to see, because that's what we saw in BizTalk when we kind of gave them a computational facade or presentation that was closer to the PyCalculus. There was a hill to climb that was harder for them. Giving them the for comprehension based approach, it becomes much easier, and they can reason, they can see their application semantics, they can see their application architecture end to end, and they can see the relationship of their code to what how the system is behaving in a much clearer way, and also get automated support to go against some of the more pernicious and difficult phenomena of concurrent and distributed programming. So anyway, so that's just a taste of monadic design patterns for distributed programming. So now I'm going to post the Hangout, the broadcast part of the Hangout link in the chat, and if anyone wants to ask questions, feel free to join, and then we'll close it out from there. So here we go. All right, so anyone who wants to join me, we've got a couple of minutes left in the session, and I'm more than happy to go run over by 5 minutes or so in the interest of answering questions. I guess I should also account for delay. Okay, it appears that no one would like to join the session and ask a question or type a question into the chat window. So I would like to close by thanking Orion for the opportunity to address you, and I hope that at some point we can do this again. I'd love to do it in a setting where it's a little bit more two-way. I feel very much like I'm talking to myself. So hopefully next time we can have a chat which is a little bit more of a dialogue than a soliloquy. But thanks again, and I hope you enjoy the rest of your Wednesday evening. I'll type my email, or Orion has my email, so if anyone wants to post me a question after the fact, feel free to send me an email. Thanks again, and hope to see you around the internet. Ciao.